Hello everybody and welcome to Mr. Saucedo's YouTube videos. Today we're going to be looking at Zumdahl the 7th edition, specifically chapter 13, which is about chemical equilibrium. All right, so take a look at this animation down here. And so I know it happened really quickly, and actually, you know what, I'm going to replay it again. So notice that what we have here is a good example of equilibrium. So we had too many molecules on the left, and we didn't have very many on the right. But eventually, the flow rate going in and going out ends up becoming equal over time, so that there's no net flow. So what is equilibrium? Equilibrium is a state where the concentrations of all of your reactants and all of your products remain constant with time. And so from a macroscopic level, it looks boring, like nothing's happening. But on a molecular level, there's a lot of activity. And so it's important to know that equilibrium is not static. It's not like, okay, great, we've reached Zen and now nothing happens anymore. So I like to think of it as you have a certain number of people that are allowed in a particular, like, let's say like banquet hall or something. So 282 people. So if you're allowed 282 people, the way I picture this relating to equilibrium is, let's say that a couple of people need to leave. So now we have 280 people. That means that immediately, there's a waiting list, two more people would go in. And so we have to keep the amount equal. And that doesn't necessarily mean the amount of individuals, okay? But from a chemical perspective, we're looking at the same rate. So you can think if there are two people leaving, that there are two people passing them by going in at the exact same time. So changing concentrations is the key. So let's take a look at the manufacturing of ammonium here. And we can see that if we look at concentration over time, this is what we see. So hydrogen is going down, right? It's decreasing. Eventually it levels off. Same thing for nitrogen. Nitrogen is decreasing. Eventually it levels off, and ammonia is increasing. Again, exactly what you would expect, right? If this is a chemical reaction, you would expect the amount of reactants to go down and the amount of product to increase over time. But eventually they're going to reach a state where everything kind of appears to stop, okay? And in that sense, now we have a certain amount of hydrogen and a certain amount of nitrogen and a certain amount of ammonia, and nothing else is going to happen macroscopically. And so that's what equilibrium is. Now the rate at which these are being manufactured, or the rate at which these are being used up, becomes equal. So now everything is constant. So instead of looking at concentration, maybe we should look at something like a reaction rate, right? So again, not only is it the concentrations of the individual molecules, it's also, the rate that is the key here. And we spent a long time talking about rate laws, right? So concentrations will eventually reach levels where the forward and reverse reactions are the same. So the forward reaction is going from reactant to product, and the reverse reaction is going from product to reactant. And so we normally kind of ignore the reverse reaction because it's normally such a small component, but at equilibrium, it's really important. So you can see the forward rate is decreasing, the reverse rate is increasing, but eventually they're going to reach a point where they are equal. And so that, again, that doesn't mean that you have the same number of molecules of reactants and products. Not necessarily. That could happen, but not necessarily. We're talking about the rate of the reaction, okay? Ends up stabilizing over time, and that's what equilibrium is. So let's take a look at the following situation, because equilibrium constants are kind of the key here to understanding what's happening in a equilibrium reaction. So here is our generic balanced equation. We have JA plus KB. Our double arrow is letting us know that there's some form of equilibrium occurring here, or at least we have a forward and reverse reaction. LC plus MD. What do these mean? So A, B, C, and D can be any chemical. So, two reactants, two products. Do you need to have two? No, you could have three, or you could have one. Again, they're just generic. What are the J, K, L, and M? They're supposed to represent the coefficients in your balanced equation. So, these could all be ones, or they could be 1, 2, 3, and 3, or 1, 2, 2, and 1, whatever they might be when you balance your equation. Now, so what is this? K is the equilibrium constant. And so this is the way we would write the equilibrium constant for this particular generic reaction. So K is equal to the concentration of C raised to the L power times the concentration of D raised to the M power divided by concentration of A to the J times concentration of B to the K. So square brackets means concentration. So this is representing, like the molarity of whatever we're looking at here. And then K is our equilibrium constant. So K, oh, it got cut off, but K is the equilibrium constant, okay? And it's normally written as a unitless number. So it's normally written as just a number. Okay, so this is also, by the way, called the law of mass action. And so what are we supposed to get out of an equilibrium expression? So an equilibrium expression is what you just saw on the previous slide, okay? It's the law of mass action applied. And so equilibrium expressions for a reaction can be written as such on the previous slide. But let's say we wanted to look at it from the opposite direction, right? Let's say the products were turning into the reactants. All I would need to do is write the reciprocal of that fraction. I could just flip the product and reactant parts. That's all I would need to do is just flip my fraction. Also, keep in mind that if I wanted to multiply everything in that by like 2 or 3, the way that you would write that would be by raising it to the power that you are now changing it by. So if, everything was, squared, let's say, if you wanted to, double everything, now it would be to the 4th power because you are literally now, you're literally taking the entire thing and you are, squaring it again or something. And so it's really important to kind of just remember that that's kind of how equilibrium expressions work. You can flip them upside down, or you can raise them, to another power, basically, if you're multiplying by a factor of 2 or 3 or 4, etc. Now, K values, like it says, are normally written without units, and K always has the same value at a certain temperature. So it doesn't matter how many or how much reactant or product you have at the beginning of your reaction. At equilibrium, the K value is the same as long as we're talking about the exact same temperature. So for a reaction, though, at a particular temperature, there can be multiple ways of getting K, right? So there's an infinite number of ways of getting K, because K is, again, a unitless number. Like, it can be anything. It could be like 10, right? And if I said, okay, give me as many ways as possible of getting the number 10, you could come up with an infinite number of ways of doing that, right? With a fraction. You could do 5 times 2 divided by 1. Like that's 1. Like that's one way of writing, and getting 10. So again, it's an interesting concept, and it requires, a lot of just kind of general knowledge before we can actually utilize it in any interesting ways. So let's talk about pressure. So that was equilibrium expression stuff. And that was dealing with concentrations normally of aqueous solutions. Now, for gases, obviously, we're going to be dealing with pressure. So K, as on the previous slide, sometimes it's called K sub C. On the AP exam, I believe they do use K sub C. That involves concentrations, like I said, molarity, right? Kp, though, involves pressure. On the bright side, it's the exact same concept. So here we go. Again, we have the manufacturing of ammonia because, we could represent these as concentrations, as, moles per liter, or we could represent them as atmospheres or some unit of pressure. So on the bright side, this is the way I would write the Kp for this particular reaction, right? So I have my ammonia, and that would be the partial pressure of ammonia squared, because my balanced equation has a 2 there, divided by, again, my partial pressure of nitrogen. There's no coefficient here, so I don't need to raise it to any power. The partial pressure of hydrogen cubed. And so if I were to write this instead, as Kc, as an equilibrium expression involving concentration, it would be the same thing, except now I'm dealing with, molarity most likely. So what if I asked you, to find the equilibrium constant? I could do that, right? I could say, hey, here are my partial pressures. Find the equilibrium constant. So plug them in. Here's what I would get. I would take my my equilibrium expression, but with pressure, And then I would just plug those in. So 2.9 times 10 to the negative 2 squared divided by 8.9 times 10 to the negative 1 times 2.9 times 10 to the negative 3 cubed. And I would get a number like 3.9 times 10 to the fourth. Notice that even though these are in atmospheres, my number is unitless. So what's the relationship between K and Kp? So there's a direct relationship between them, which is kind of nice. Kp is equal to K times RT raised to the power of the change in N. Okay, so what's RT and what's N? I guess we should probably talk about N first, since, R and T, we've done gas laws. We kind of know what RT means. So delta N is the sum of the coefficients of your gaseous products. So not liquids, not solids. We're talking about gases here. Minus the sum of the coefficients of your gaseous reactants. So it's products minus reactants. That's what that would be. Yes, it can be a negative number, obviously, right? Because it's products minus reactants. So it's possible that you have, more reactant than product in the gaseous state or something like that in your balanced equation. So R and T, what are those? Well, R is our universal gas constant. It's in liters times atmospheres per mole Kelvin. And then T is the temperature. And yes, the temperature has to be in Kelvin. So let's use that. Here's the same exact equation, right? Now, let's use what we just found. So we found that the equilibrium constant for the pressure of this is 3.9 times 10 raised to the fourth power, right? So let's calculate that at 35 degrees Celsius, okay? So what do? I have my Kp right here. K is what I don't know, because that's what I'm trying to find. I'm trying to find just the regular K value. I have right here our R, and I have our T, and then I have 2 minus 4. Why 2 minus 4? I have 2 moles of gas on the product side here. I have 4 moles of gas on the reactant side, right? 3 and 1 is 4. So by plugging this in and solving for K, I would get 2.5 times 10 to the 7th. And I'm not going to go into the mathematical kind of manipulation there, because it should be pretty easy, right? 3.9 times 10 to the fourth divided by this entire thing, making sure that you don't make any mistakes when you're plugging it in, because otherwise you'll get a totally different value. Notice it is unitless, though. Even though I have, atmospheres, liters, moles, all this stuff is going on, the answer is unitless at the end. All right, heterogeneous and homogeneous equilibrium. So there are two types of equilibrium. A homogeneous equilibrium means that we have the same states of matter. Okay, the same state of matter. They could all be aqueous or all be gaseous, something like that, right? So right here, the one we've been using is an example of a homogeneous equilibrium. I have all gases. Another good example would be something like this, where I have all aqueous solutions. So that's called homogeneous because, again, remember, homo meaning same. So we have the same state of matter, basically, in our chemical equation. Now, a heterogeneous equilibrium means that I have more than one phase. And so that could be solids and gases, or it could be liquids and gases, something like that. Those would be examples of heterogeneous. Hetero meaning different. So why is it important to know the difference between a heterogeneous equilibrium and a homogeneous equilibrium? Well, heterogeneous equilibrium, does not depend upon solids and liquids that are present in your reaction. So the short answer of why we don't include liquids and solids in our equilibrium expression is because they have a constant concentration that doesn't change. Aqueous and gaseous equilibrium can change in concentration, whereas pure liquids and solids can't. So let's say I have this balanced equation, okay? Notice I have only one reactant, and it is a solid. I have two products, one of which is a gas and one of which is a solid. So if I wanted to write the equilibrium expression for this, okay, right? Most people would assume I would do KCl squared times, O2 cubed divided by KClO3 squared. Totally reasonable, right? But I don't include liquids or solids in my equilibrium expression. So in reality, this is what it would look like. I just basically ignore these and I just write down the gases or aqueous solutions. Again, I know it seems odd, but the reason why this works is because the concentrations of these in an equilibrium expression should be constant numbers. All right. Extent of reaction. So what does K tell us? So if the value of K is a very large number, almost infinity, not even that though, right? It could be like 100 or whatever. If it's much larger than 1, that means that our products are going to be in high number. In other words, the equilibrium lies to the right. So again, we have a double arrow. You can picture that the right arrow is really the direction that this, equation is going. That means that the reverse reaction is very small. And so essentially the reaction goes to completion. So if you are a chemist and you are wanting to do an experiment, if you want something that is, going to give you the most bang for your buck, you want something that is going to have a large K value, because then you don't have to worry about the reverse reaction. So what I always like to say is that that is a product favored reaction if you have a K value that's larger than 1. Now, what if we have a small value of K? If we have a small value of K, that means that our equilibrium is mostly going to be on the left side. So again, we have a double arrow. You can picture we're going to be basically breaking apart our products quicker and making more reactants. So essentially the reaction does not occur. So a lot of, reactions that are totally unlikely to happen actually have equilibrium constants that are very small values, which means that they're extremely unlikely. It doesn't mean they don't happen. It just means that, your reactants are stable. And so I always call this a reactant favored reaction. In other words, though, the reaction does not occur. Now, why do we think that K can determine this? Can anybody kind of think about this? Why would K affect the direction that our equilibrium is, whether it's to the right or to the left? Well, remember, this is what our equilibrium constant is. It's products over reactants. So think about this. If the concentration of your products is a high number and the concentration of your reactants is a low number, K is going to be large. On the other hand, if your reactants are a large number and your products are a small number, you're going to end up with a tiny value of K. It's really just the way the fraction works. Because products are on top, if products are large, you're going to have a big K value. On the other side, if reactants are large, you're looking at the bottom part of that. And yes, we ignore solids and liquids though. So remember, this only applies to gases and aqueous solutions. So, you could have crazy amounts of solid and liquid, but the equilibrium constant doesn't depend on those. It only depends on the gases and the aqueous solutions. So let's talk about Q then, right? So K is our equilibrium constant. Q is called the reaction quotient. And so that is when our initial concentrations are non-zero. And so we still apply the same equilibrium constant stuff that we've talked about, the law of mass action, using the initial concentrations instead of equilibrium concentrations. That's the difference between Q and K. K is at equilibrium, Q is not at equilibrium. So law of mass action still applies, except instead of K, you can replace that with a Q. Let's actually do something with this though, right? So what if K and Q are the same? That means your system is at equilibrium, no shift is going to happen. That doesn't mean that it's boring though. Remember, it's a dynamic equilibrium, so a lot of stuff is still moving back and forth. It just so happens to be the rate is constant. If Q is greater than K, the system is shifting to the left, okay, consuming products and forming reactants until equilibrium is achieved. Okay, so again, we're moving to the left if Q is greater than K. What if Q is less than K? Then the system is shifting to the right. That means it's consuming reactants and forming products to attain equilibrium. So you can really just think of these as opposites, and it can let you know which direction you're going to see movement in. Is it going to move to the left or is it going to move to the right? So let's actually use this, and we have to do some wonderful math for this, okay? So we have a very simple reaction. We have an iron 3 ion, we have thiocyanate. We're making, an iron thiocyanate complex basically, okay? So I have 6.00 moles per liter of my iron 3 ion. It is aqueous. I have 10 of my, and again, moles per liter, of thiocyanate, also aqueous. I'm mixing them at a certain temperature, and at equilibrium, I measure the concentration of this complex, which is also aqueous, to be 4.00 moles per liter. What is the value of the equilibrium constant for this reaction? All right, let's look at the keys here. So this is my amount of this. This is my amount of this. And this is my amount of this at equilibrium. So this is the amount that I'm starting with. At the start, there should be none of this. None of this is formed yet. But at equilibrium, I know what this becomes. So how do we do this? We set up an ICE table. So an ICE table is an acronym for how we can mathematically use a matrix to kind of figure out what's going on. And it's a great way to stay organized. So I always write, or you can write your equation above it. And then I stands for initial. What are our initial concentrations? So we have 6 moles per liter here. We have 10 moles per liter here. Okay, it's a little crooked, but you get the idea. That's the thiocyanate. And 0 for this complex. What's the C? The C is the change, okay? How much is it changing by? Well, if we know that the equilibrium concentration of this is 4, that must mean that this changed by 4 and this changed by 4. And it is subtraction. We are losing our reactants. We are making product. So when I do that, what I get is 2 moles per liter of this, 6 moles per liter of this, and I have at equilibrium 4 of my complex. And so now I can plug that into my equilibrium expression. So thankfully, these are all ones, right? So in the sense that I don't have anything squared or I don't have anything cubed, but they could be. And so I just plug that in. So 4 divided by 2 times 6, and I get 0.333. Okay, it got cut off, but it's 0.333. Okay. So I now know what K is. Now let's do an extension of that. Trial 2. I start with 10.0 moles per liter of this. I start with 8 moles per liter of my thiocyanate, same temperature. At equilibrium, how much of this am I going to have? That's a little bit harder, but I can use an ICE table to do it. All right, so still set it up the same way. What is my I? 10, 8, 0. What's my change? I don't know my change. I know this is going to be, gaining some amount. I know these are going to be losing some amount. So what's my equilibrium? It's, 10 minus some amount. 10 minus x, 8 minus x, just x for that. I can plug that in still, though. So if I know k, which I found from problem number 1, is 0.33, then I can set that equal to x divided by 10 minus x times 8 minus x. This is solvable. I can find x. I mean, it's a mess, but I can find x. So here's what I would do, right? I would multiply everything through. Yes, you probably never thought you would ever have to FOIL anything in your life, but literally something from like algebra 1 is actually useful here, right? We're going to do our outside, our inside, that whole thing. And I'm just going to remind you of how to do that, right? So we have 0.33, and now I have my nice little, quadratic basically here, right? At least I think that's what it's called. And so we've got our polynomial. Again, I'm not a math teacher. So I multiplied that through, and now, I want to multiply this through. I need to multiply by my k value here, by everything, and I need to get x by itself. So I need to get x by itself. I need to remove this x because it needs to be equal to 0. I need to be able to solve for x. Is there anything you can think of that we could use to solve for x? Oh man, it's the quadratic equation. So minus b plus or minus the square root of b squared minus 4ac divided by 2a. Again, something else you thought you would never use in math actually is useful. So let's solve for x. I'm not going to plug all of this in. I mean, you're more than welcome to do that on your own, okay? What does x end up being? Well, again, we have plus or minus, right? So we're going to get two roots. We're going to get two answers, one of which is going to be possible and one of which is going to be impossible. So you get two answers. You get about 5 and you get about 16. 16 is impossible because if I subtract 16, I get negative values. So you can't have negative values for something. 5, though, I get positive values. So the answer that I was looking for was 5. Now, that doesn't give me a crazy amount of information there, but the answer is 5. So how do I use logic really to solve an equilibrium problem? So the first thing you need to do is you need to write a balanced equation for the reaction. So for the previous one, it was balanced. It was 1, 1, and 1. So that was nice and easy. Once you've done that, you want to make sure you can write the equilibrium expression using the law of mass action. Again, balanced equation is the key because if you put a 2 as a coefficient in front of something, you have to square it. List your initial concentrations. Calculate Q if necessary to determine which direction our equilibrium is going to shift. Find the change needed to reach equilibrium, and that's again the change that we're talking about, the C in our ICE table. Substitute equilibrium concentrations and solve for your unknown. Like that's literally what you do every single time. And at the very end, you probably want to check to make sure that your equilibrium concentration is correct. And it says make sure they give the correct value of K. So you want to make sure that if you're given the K value, you plugged that in correctly, or if you're finding the K value, that it makes sense. All right, let's do more of this. Okay, here's another really good one. Consider the reaction represented below, so same exact equation. Trial 1, 9, 5, 1. What are the equilibrium concentrations for these things? Remember, I know what K is, so we're pretending like we're using the same K value. So 9, 5, and 1, can I find that? Of course I can find that. The ICE table is the key. So if these are my initial concentrations, now remember, because I'm starting now with this amount, this is really a Q problem now, right? It's a reaction quotient because we're not at equilibrium. So what's the change? Minus x plus x. So at equilibrium, 9 minus x, 5 minus x, 1 plus x. I know that again, it's my product divided by my two reactants. I don't have to worry about squaring anything, which is nice. So I have my 0.33, and I would set it equal like this. Yes, we're going to have to use the quadratic equation again. All right, so let's solve that. So 0.33 times this, I need to FOIL it, equals 1 plus x. This is FOILed out. I can multiply everything by 0.33 on this side of the equation. And now all I have to do is subtract 1, subtract x, and now I have 0 on that side. Now, once I have that, I have to use the quadratic equation again, everybody's little nightmare, in order to get what x is. And so again, I'm going to be given two roots. So 3 is possible, 14 is not, because again, I would end up with a negative value. Now, that is not what it asked me to find. It asked me to find something else. So if we go back to the original question, I would now need to actually plug this in and subtract everything and add it together. So it asked at equilibrium, what are those concentrations? So at equilibrium, the concentration of iron 3 plus is 6. Thiocyanate is 2, and this complex is 4. Always go back and check you're actually solving for the correct thing. Because a lot of times people are like, oh, I did all this work. Great, here's the answer. All right, that's not what it was asking for, though. There was still one more step to do. All right, another good equilibrium check here. I have a 2.0 mole sample of ammonia introduced into a 1.00 liter container. At a certain temperature, the ammonia partially dissociates in the following equation. At equilibrium, 1 mole of ammonia remains. Calculate the value for K. All right, first things first, I need to balance this equation. All the other ones we've dealt with were all balanced already. This one is not balanced. So always balance your equation first, because I'm now going to have to square this and I'm going to have to cube that. So that's really important when I write my equilibrium expression. It's giving us a lot of information here. 2 moles, 1 liter container. That's a molarity of 2. At equilibrium, we have 1 mole in 1 liter. That's, again, 1 m, right? So 1 mole per liter. All right, let's set up an ice table. So 2, 0, 0. How do I know that? Again, it's telling me I start with this. It's an empty container, so I don't have anything here. Change, okay? How do I know I'm losing 1? It tells me at equilibrium it's 1, so I have to lose 1. Now, here's where it gets tricky. This has a 2 in front of it. It's double. This doesn't. This has a 3 in front of it. So what should the change be? The answer, half, right? This is double. So what's half of this? It's 0.5. And yes, it's positive because I'm gaining products. I lost reactants. All right, so that's kind of nice. Well, what about for 3 then? Well, it would be 1.5, right? You can kind of think of it as this is like our x here, right? 0.5. This is double. This is triple it. Like it all has to be equal though, right? Like everything has to kind of make sense. So this would be plus 1.5. All right. I can plug that into my equilibrium expression. Yes, I still would have to raise them to the correct powers. So 0.5 raised to the 1, nice and easy. 1.5 raised to the 3. And, well, 1 raised to the 2 doesn't really do anything, but still I can find that to be 1.69. There you go. So very, very, very weakly product favored. Like not even, right? We're almost already at 1. All right, let's try a different one. What if I have 1 mole of N2O4 in a 10-liter vessel and I allow it to reach equilibrium according to the following equation? All right, calculate the equilibrium concentrations and it gives us a K value. Perfect, right? What's the key? 1 mole, 10 liters. That's 0.1 moles per liter. Don't forget. This is the K value. All right, again, and notice it's already balanced. That's kind of nice, right? Already balanced for us. Let's do this. Initial, zero point 0.1. Remember, moles per liter. So don't just plug in 1 or something. It has to be in moles per liter. It has to be in concentration. 0, I don't have any of this to start with. Minus x plus 2x. Again, why? Double, right? If this is going down by x, this has to go up by 2x. 0.1 minus x, 2x. I can plug all of this in. That was my actual value for k, 2x squared. So in reality, 4x squared would be what this would actually be equal to. 0.1 minus x. Again, x, I'm not going to go through any quadratic stuff. You end up getting 0.0044. Not what it was asking for, though. So now I actually have to calculate it. So 0.1 minus 0.0044, that gives me 0.096 moles per liter. This I would have to do double, so 0.0088 moles per liter. Now, this is the exact answer for this. A lot of times, especially in chemistry, and professors will tell you this, save time, don't do the quadratic equation if you don't have to, but I'm just showing you the complete method of doing so. Last but not least, Le Chatelier's principle. If a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction to reduce that change. I always say it's applying stress. If you're applying stress to a chemical equation that's in equilibrium, it will try to relieve that stress however it can. So what are the 3 ways that we can affect a system? Well, concentration is one way. If you add something, it will try to shift in a way to remove that component that you added. On the other hand, if you remove something, it will try to make more of whatever you removed. Temperature. K does depend upon temperature, but really the only thing you need to worry about here is endo versus exothermic. In an endothermic reaction, energy is a reactant. In an exothermic reaction, energy is a product. And I'll give you some examples of that in a bit. For pressure, it's a lot weirder. The system will shift away from the added gaseous component. So if you add a gas, it will try to remove that gas. If you remove a gas, it will try to replace the gas and make more of it. of whatever you removed. Now that's only true of non-inert gases. If you add an inert gas like, helium or something, it will not have an effect on the equilibrium at all. What if we change the volume, right? Because pressure and volume are directly related since we know all about gas laws. If you decrease the volume, then that means that it's going to try to move in a direction so that it will go towards a side of the reaction where there are fewer moles of gas. All right. I know that was a lot. Let's talk about that. So we have this balanced equation here. Which direction is the equilibrium going to shift? What if I add more here, right? So I'm applying pressure here. If I add more, it's going to move to the right. It's going to try to remove what I added by making more ammonia. What if I remove some nitrogen gas? It's going to try to replace that. So it's going to break apart some ammonia to try to replace the nitrogen that I removed. What if I add H2? What if I add some hydrogen? It's going to move to the right. It's going to try to make ammonia in order to remove the hydrogen I added. What if I remove it? Well, then it's going to try to replace it. So the ammonia is going to break apart and it's going to try to make more hydrogen. What if I add more product? If I add more product, it's going to say, hey, I already have enough product. I'm going to move away. I'm going to break it apart into some reactants. What if I remove the product? Well, then it's going to move to the right. It's going to try to replace the product that I actually removed. So this is a method that chemists use in industry to maximize their output. Think about this, right? What if I said, I want you to make as much ammonia as you possibly can? What are some things you could do? Well, you could add more nitrogen. You could add more hydrogen. That would definitely make more ammonia. Also, though, you could remove ammonia. As you make it, if you remove it, the reaction is going to continue to move towards making more ammonia. All right, what about some examples that use something we talked about earlier? So what if I add some carbon to this reaction? Spoiler alert, nothing's going to happen. It's a solid, remember? Only gases in aqueous solutions affect equilibrium. What if I remove some AS406? Nothing, it's a solid. What if I add some more AS4 here? It's going to move to the left. It's going to try to remove what I added. What if I remove some CO? It's going to try to replace it. It's going to move and try to make some carbon monoxide. Now, what about heat? Okay, so remember, in an exothermic reaction, heat is a product. And in this case, heat is a product. So which direction is the equilibrium going to shift? Well, what if I heat it up? What if I increase this? If I increase this, it's going to say, all right, I'm going to move the opposite direction. So it's going to move to the left towards the reactants. What if I decrease it? What if I remove heat? If I remove heat, it's going to try to replace the heat. So again, if you have an exothermic reaction and you want to get your reaction to go to completion, you can basically cool it off with like an ice bath. So you can take this and you can cool off the chamber, and that is going to make it move towards your product side. It's going to start manufacturing more ammonia because as you manufacture ammonia, you manufacture heat. A very simple fix. Or what about an endothermic reaction where heat is a reactant, right? Because remember, endo means in, right? Heat is moving in, so that would mean it would be a reactant. So if I increase the temperature of an endothermic reaction, you're going to undo it. You're going to basically make more product. On the other hand, if you are going to cool off, right, decrease the temperature, now you're going to end up making more reactants instead. So if you want more product, and it's an endothermic reaction, you can heat it up. If you want more product and it's an exothermic reaction, you should cool it off. All right, so that was a long one, but if you have any questions, let me know. We'll be moving on to the next chapter soon.